Okay, so let us start today's lecture. So, we were discussing fluorescence spectroscopy, right. After UV visible, we looked at the basic concepts of fluorescence. So, fluorescence is all about returning the electron from the excited state and giving radiation, right. When they return, there are many many competitive process which are non-radiative kind of. Non-radiative kind of means like they do not emit light, and therefore, they are not contributing to the signal. So, those are non-radiative process that we had looked at. What are those? It is internal conversion, right. Yeah, so we are discussing fluorescence. In fluorescence, we have we started looking that when electron goes, which is time scale of femtosecond, and when it return back, what happens. So, when it is returning, there are many way it can return. Some are non-radiative, few are radiative. Non-radiative process where the light is not emitted, right. So, like internal conversion, heat dissipation, quenching, many of these are non-radiative, intersystem crossing. Few are radiative like a fluorescence, phosphorescence. So, those are the radiative process. We had looked at briefly what is photoluminescence because of the light shining and some radiation is coming. Emission typically which gives rise to fluorescence and phosphorescence, and we had initially looked at absorption, which we can call it excitation. So, to sum up what we have looked at, it is a fluorescence spectroscopy stands apart from many other analytical technique because it is a unique ability to detect and quantify how much light is coming. That is a quantification is very important, and that offers the distinct application because it is a quantitative technique, right. And if we compare to other technique, it is a quantitative, it is a sensitive. So, let us compare fluorescence and UV, that UV visible spectroscopy, right. We have discussed this UV visible. So, unlike UV visible which measures the absorbed light, right. So, how much light we are shining, how much photon is getting absorbed, that is what UV visible does. Fluorescence detects the emitted light, that is the difference, not absorption, but emission light. It is a more selective and sensitive, right, for low concentration biological molecule, right. It is a it is because it is a electronic spectrum. If you remember in the first class we had discussed how a technique can be sensitive. It depends upon the Boltzmann distribution, how many particles are on the ground state and how many are in the excited state. So, in this case, since it is electronic spectrum, it is a sensitive compared to many other techniques like a vibrational, rotational, nuclear magnetic resonance. It is a sensitive technique, it is a quantitative, so it has an advantage. Fluorescence versus phosphorescence. So, here if you remember there are two radiative processes coming from S1 to S0, that is a fluorescence, coming from T1 to S0 is phosphorescence. Fluorescence is fast, nanosecond time scale, phosphorescence is millisecond time scale, slow one, right. But important discussion is S1 spin was like that and it returns like that, and it has flipped it. So, it is a this is allowed transition, this is not allowed transition. So, that has a low probability, it is a forbidden transition and it takes longer emission lifetime. Fluorescence molecules basically it is a sensitive because there is no forbidden transition happening. So, it is sensitive, it is fast and you can detect it easily. Now, fluorescence versus chemiluminescence. Unlike fluorescence, chemiluminescence requires external light excitation and chemiluminescence produced because of some chemical reaction is happening, right, chemical reaction happening. So, without even bioluminescence, some biological reaction is happening like Jugnum we have seen it. So, those are some reaction happens and then the light is emitted. Here there is no reaction happening, just you are exciting and emitting. and fluorescence versus other spectroscopy like FTIR, which we are going to look at in the coming class. So, fluorescence gives electronic information and therefore, it offers the high sensitivity energy gap, right. If you look at here energy gap that we have looked at S0, S1, fluorescence is happening from here to here, IR is happening in vibrational state. So, energy gap is less compared to this one. So, therefore, fluorescence is more sensitive, more quantitative, fast, it offers the dynamic information, structural information, right. The structural information, it gives you idea about even 3D structure of a protein. So, to sum up what we had looked at yesterday, this is called Jablonski diagram, electron going from ground state to excited state. So, it is excited singlet state we call it, excited singlet state. It returns by non-radiative process which is called internal conversion. Time for this is femtosecond, time for this is 10 to power minus 15, 10 to power minus 14 to 10 to power minus 11, and then it can come also by quenching or something called non-radiative process which is typically slower. Fluorescence is nanosecond and sub nanosecond, and then we have a quenching which is again non-radiative process. When it returns here T1 state, this is called excited triplet states. Now that's when it comes from here again radiative process, it is in millisecond. We have also discussed it can go back to here, right, triplet, right, like this, it can go back, that is again it takes time. So, therefore, whatever comes from here it is called delayed fluorescence, right, and this is the time scale, right. So, non-radiative does not give you light, but fluorescence is nanosecond, phosphorescence is millisecond to millisecond or 2 second can be happening, and then you have an internal conversion, non-radiative absorption, again it is absorption or excitation, right. So, that is a time scale of this motion. What time scale says? So, why I am emphasizing on nanosecond or even microsecond? Time scale, right, time scale of the fluorescence that is happening. What is the good part of that? Good part is that you can monitor the reaction that is happening in nanosecond time scale, or even if you can, if some reaction is happening in femtosecond, can you monitor using fluorescence? No, that is too fast than fluorescence lifetime. So, if something happen in say nanosecond to microsecond, probably you can monitor it, and most of the reaction happens in this time scale. Reactions mean like a protein ka domain movement happening in microsecond to nanosecond time scale, those can be monitored using fluorescence spectroscopy. So, these are the time scale that already we have discussed. Again, just want to emphasize absorption femtosecond, fluorescence nanosecond, phosphorescence millisecond, 2 seconds, that is an important time scale you have to remember. Just to sum up, what is the difference between fluorescence and phosphorescence? One is coming from singlet state, another is coming from triplet state. It is a very fast nanosecond, that is comparatively slow, that is a millisecond, right. A typical lifetime of fluorescence is in nanosecond 2 to 10 nanosecond, phosphorescence typical lifetime to millisecond to second, and there is no specific requirement for fluorescence to happen. Only specific requirement is the molecule should fluoresce and it should have a substantially or reasonable quantum yield, right. It mostly occurs in solid state and low temperature phosphorescence. We had also briefly looked at, but this is the Stokes shift. So, Stokes shift means like a absorption and emission are shifted by few wavelength, because when it goes to higher state, but chup chap it comes to the some lower excited state, from there it comes. So, your wavelength is always higher in emission compared to excitation. The shift in the wavelength was observed by Stokes, and that is called Stokes shift, right. And actually even solvent, there is solvent effect of excited state that also can contribute towards such kind of shifts, right. So, I have also looked at that emission wavelength depends upon the relaxing back to lowest vibrational state, which is here. So, it comes back by non-radiative relaxation, then it comes back, right. So, for a molecule, the same fluorescence emission wavelength is absorbed irrespective of whatever excitation happening. Important point that we had not mentioned it. You can excite using different laser source from here to here, or here to here, or here to here, or here to here, but when it is coming back, it only comes from here, but it can come to different vibrational state. So, that means the whatever excitation wavelength that you use, emission is going to be same, right. Irrespective of excitation wavelength, emission is going to be always same for a molecule. So, excitation maxima can be there, right, but an emission maxima can be also there. But if you say a molecule has a emission maxima at 4 or 530 nanometer, whether you excite at 400, 410, 420, wherever you excite, emission is going to be same 530. Is this clear? I will de-emphasize on mirror image rule. Mirror image rule says that your excitation and emission are identical, but opposite, right. So, vibrational wavelength in the excited state and ground state are similar. So, any absorption spectra reflects that vibrational level are electronically excited state, and emission spectra reflects that vibrational level of the electronically ground state. So, fluorescence emission spectra is mirror of excitation spectra, something like this. So, that means if we are exciting from here to all the higher vibrational state of electronic excited state, it comes back from V0 S1 to the ground states. So, if you plot the spectra, this is for absorption and this is for emission, this is our Stokes shift. So, it is like mirror, it is like a mirror, a spectrum is like mirror. So, here is absorption spectrum, this is emission spectrum, right. So, that is the coming back to. So, mirror image typically happens when it comes from S0 to S1 and returning from S1 to S0. अगर S2 में गया तो that comes to S1 and then it comes back. So, that part will not be considered as like here. So, this is happening S0 to S2 absorption, and this is absorption is S0 to S1, but when it return back it comes like this. So, if you just take this one, it is a mirror of that. S0 to S2 is not contributing towards emission of the fluorescence, right. So, it is a just one way, like a one way traffic is there, it has to come to S1 V0 and then return back to the ground state, that is a mirror image rule. Quantum yield is number of photon that is emitted by number of photon that is absorbed. So, it is always less, right. Quantum yield is never 1, because not all proton gets emitted, it gets lost in non-radiative process like internal conversion, the quenching, intersystem crossing, heat dissipation, wherever. So, in practice you can measure it, the quantum yield can be measured, and जितना ही अच्छा quantum yield होगा fluorescence और fluorescent molecule उतना ही अच्छा होगा, because you require less light and it is more sensitive. So, in practice it is measured by comparative measurement of reference compound, for which one has determined the quantum yield with high accuracy, right. So, we discussed out of our 3 favorite amino acids that absorbs: phenylalanine, tyrosine, tryptophan. Tryptophan has a high quantum yield, tyrosine comparatively quite less, and then phenylalanine is not fluorescent. So, that is a use of quantum yield. So, all the time scientists or even the company, it is a commercially very lucrative business, right. You can synthesize a fluorescent molecule selective to excitation and emission, because you want, sometime you want a red fluorescent tag, you want a green fluorescent tag, a blue fluorescent tag, a yellow fluorescent tag. Why you want this? Why you want this such fluorescent tags? होली का कलर थोड़े बनाना है, को लोकलाइजेशन देखने के लिए, सेल के अंदर हमें देखना है. So you require to put your tag with a different color inside the cell, and when these two protein come together, you know that these two color are coming together. Therefore, you require different kind of fluorescent tag to be attached to your biomolecule, and then we can see inside even cell, right. Inside the cell you can see all the phenomena. Therefore, this getting the good fluorescent is always a very important one, right. So, ideally reference compound which you are using for measuring the quantum yield, like same absorption as compound of interest of a given excitation wavelength. For this reference compound, excitation and emission characteristic should be same like compound of our interest, and like then if it is not same, then there is instrument dependent and all those. You have to have a same solvent, and also refractive index you have to be same, right. So, that is a characteristic of a quantum yield. Quantum yield of a fluorescence depends upon what biological environment is. Your same tryptophan in different biological environment can show a different. There is an intrinsic quantum yield, and there is a intrinsic quantum yield whatever, and there is external factors that contributes, right. So, presence of concentration. If the two fluorescence it is a too high, then you have a self quenching. So, you like a concentration plays an important role. Use of solvent, different standard or different solvent also plays a role, and then you have to determine in this case using a standard sample what is the quantum yield for a fluorophore. So, you see, just looking at the quantum yield, we can think of an experiment. What experiment? First two experiment you can think of. I am saying depends upon the environment, right. Environment, tryptophan is here, high fluorescence or low fluorescence. If it is like this, environment is changing, right. Here free, here in the say hydrophobic, like tryptophan is a hydrophobic amino acid, right. So, it will be buried inside the hydrophobic core. So, its local environment changes, and therefore, fluorescence changes. So, if you just measure the emission spectrum and quantum yield, you know where my tryptophan is, right. If you just open the protein, कैसे open कर सकते हैं? By denaturing it, heat, urea, acid, denature, your fluorescence is changing. So, absorbing the fluorescence intensity, which essentially giving you quantum yield, you can learn a lot about the environment where tryptophan is buried. This also I had mentioned, but let us look at very carefully today. Lifetime, fluorescence lifetime, this is extremely important parameter that it has. So, lifetime is a fluorophore that spends in excited state, right, before emitting a photon and returning to ground state. We have sent the like a electron to the excited state. Now, it has to emit the photon. How much time is spent there in the excited state? That is a fluorescence lifetime. So, fluorescence lifetime can vary from picosecond to hundreds of nanosecond, depends upon where the fluorophore is there. So, here we are using excitation pulse. Abhi thoda like we are using a fancy experiment where we are not using the so called UV visible lamp, but we can use a light, laser light. So, if you look at here, the wavelength is relatively sharp, went there. It can come back like a this, or it can come back like a this. It is slowly decaying, this is fast decaying. So, slowly decaying means fluorophore has a long lifetime, आराम से नीचे आ रहा है. This is very fast decaying, it has a short lifetime. So, fluorescence lifetime, now you remember fluorescence lifetime is also very important, extremely important probe. Why? It reports किस environment में बैठा हुआ हूँ, but when it is coming fast or it is coming slow. You can learn a lot about the environment of a fluorophore. You can basically measure the decay of intensity, and you can plot I by I0 e to the power t and tau. So, this is a const, like you can 1 by e equal to tau, and you can find it out the lifetime, this is time taken for decay, you can find out the lifetime of a fluorophore, that is a fluorescent lifetime, right. That is what one can do it. So, it is a characteristic for a fluorophore, but depends upon the environment. It provides additional dimension of information missing in integrated steady state fluorophore. Steady state means just measuring the intensity, right. That is it. Here is the dynamics, the time we are measuring how it is decaying. Typically when you go and do experiment, just excite kiya, emission spectra le liya, that is a steady state. And here you excite with a pulse, let it come. So, what we are doing? We are counting the photons as it comes, right. In the previous experiment, if you remember what we are plotting, photon count when it comes. So, abhi wo 20 lakh wale mein nahi hoga, right. Last study we discussed what is the amount of the money or the amount that is needed to do a fluorescence spectroscopy. We said 20 lakhs is okay. Now, what we are putting here? Think about it. What we are putting here? A laser, right? Laser light. Laser light we are putting, we excited in a solution, and then we want a sensitive detector which counts the single photon that is coming out. So, that requires some investment, and then this kind of which does the single photon counting is a costly business. So, but it is a sensitive to biological microenvironment including pH, oxygenation state, binding and all those, and lifetime is unaffected by variation of excitation. Wherever you excite, emission does not matter, only it reports about the environment where it is sitting, right. And it is a even you can do in a clinical setting, fluorescence lifetime measurement, you just require to shine the light and you can get the lifetime of that fluorophore. All depends upon the Heisenberg principle. Okay. So, momentum and position we know, right. Similarly, there is a relation between energy and time, right. So, energy and time delta E into delta E H cross by. So, this also follows the lifetime of the like a Heisenberg uncertainty principle. So, it if you can like one of these you can determine energy or time. Now, effect of fluorescence emission, suppose an excited molecule emits fluorescence relaxing back to ground state, right. So, if the excited state tau is too long, then emission will be monochromatic. You go back here, that is what I want to emphasize upon this. If the time is taken fast, del like a t is here, what will be the energy is like this. If t is short, then it is like a broad, right. So, that is what it shows. So, depends upon if the lifetime is too long, then emission will be monochromatic, means very sharp single line. If the excited state lifetime is too short, your emission will have a wider range of frequency, that means multiple line, something like this. So, emission lifetime of fluorophore with a long lifetime you have a sharper line, and if it is short lifetime you have a broader spectrum. So, even looking at the shape of this spectrum, you are learning how much lifetime is, where it is like a it is a relaxing slow or relaxing fast. So, quite a bit of information is just coming out from here. Do you have any question?
Sir, which one is better for us or which one is better for biology?
So, the question is which is better for the experiment? Everything is better for experiment, right. You are not tuning it, let protein behave as it is, you are just measuring it. So, if your fluorophore is sitting which is relaxing slow, your spectrum will come something like this, and you can report that my fluorophore is relaxing slow. If your fluorophore is sitting where it is dissipating very fast energy, you can get this spectrum and you can know. So, let the protein behave as it is, you are just sakshi bhav se dekho what is happening, you are not getting involved into that, just observing what is happening and let it happen, right. We design the experiment as of the requirement of the protein. Yes.
Where is phosphorescence currently used in research?
Where is there are some like in where is phosphorescence used? Basically, as I said, many of the solid effect like a solid sample, phosphorescence is also used, or luminescence. Suppose you are making a quantum dot for an example, right? You use those kind of experiment, phosphorescence or photoluminescence you use in quantum dots. Quantum dots सुना है? कहाँ use होता है? Where we use quantum dots? हाँ? Yeah, many of such places quantum dots are used. So yeah, so you can use in cancer drugs. There are many application of quantum dots where sensing mostly it is used, and you can use those kind of, or in a solid material, right, in solid state physics or materials, this phosphorescence property used. For most of the biological applications, since biology is happening in cell or in solution, we mostly prefer fluorescence because of its advantage, that right. So, we started our class explaining this all spectroscopy is light matter interaction, and we are still doing light matter interaction. Luminescence, it is a light emission from substance, that is a light matter interaction. From electronic excited state, light interacts with a matter by absorption, emission, scattering, right. Absorption is just photon excited, emission is photon returning back, photoluminescence, emission using optical excitation. So, all of these are essentially light matter interaction, that is what where we started. This absorption theory we have already discussed in detail, so I will skip that. Emission theory is where we are doing fluorescence spectroscopy determines the sample concentration. You can use it quantitatively where how much light comes. So, you can essentially put it the quantum yield by I0 into the emission this variance of Beer-Lemberg law that we have put it. So, Q is quantum yield, E is absorption coefficient, I is incidence light and I that light pass through it, right. So, you can use this as a quantitatively to measure even it. In higher concentration the linearity goes, and therefore, you as we discussed that absorption or emission it is a linear in certain concentration, right. So, we already discussed there, like when we are doing quantitative you have to take factor that excitation can happen at any wavelength, but emission happens only to ground state. So, it can de-excite, photon can be emitted and fluorescence phosphorescence can happen. So, just to emphasize, when we are doing quantitative estimation you have to take care of excitation, photoluminescence, emission and all those competitive process that is happening. So, let us I would say we will go to now some of those the application of that. So, to conclude here the part that absorption is essentially excitation, right. In UV visible we frequently use the term absorption, in fluorescence we use the term excitation. Emission is relaxing back to the ground state. So, if I use relaxation that means it is a emission. Stokes shift, energy loss that happens between the higher state and coming back to S1 state. Molecule can relax to the lower vibrational state, emission at a lower energy, and it reduces the absorption and improves the signal detection. So, that is more or less we have discussed. That is a conclusion. Fluorescence is a powerful technique, studies fluorescence emission by sample when it is exposed to light. Method is subset of electromagnetic spectroscopy that we are discussing, focusing especially on light that is emitted, and yeah. So, that is the emission is important. Then there is a Stokes shift that we already discussed. An instrument basically measures the emitted light. So, depending upon what is the rigor of the experiment, one can choose how we are doing it, and it has application in various fields, whether it is biochemistry, medical diagnostic, environmental monitoring, forensic science, material science, because it all quantifies and detect it in a very sensitive manner. That is the fluorescence spectroscopy. Now, I will give you some real life example of fluorescence where we are going to use it. Okay. So, that is the conclusion for basic theory of the fluorescence, but theory is huge as we discussed. Thank you very much.